Hello people, so today I want to explain to you how to solve the next probability question. So what is the expected number of die rolls until you see all numbers? And the order doesn't matter in which you see these numbers. So we start by denoting a variable x to be the expected number of rolls until you see all numbers. So this is exactly what is asked in the question. And we can write this variable to be equal to the expected number of rolls to see the first number, any number, then plus the expected value to see another number, which is not the first one, and plus the expected value to see another number, which is different than the first and the second one. So this will be the sum of 6 expected values. And each of these expected values will have a different probability of success. Let's say the first one has a probability of success P1, the second one has a probability of success P2, and so on until P6. And what exactly we have here? So the first expected value, EX1, is the expected number of die rolls until you see any number. So the first one is pretty obvious that is 1, because how many rolls you need to see any number? You just need one roll to see any number. And what about the second expected value? The second expected value, we don't know it yet, but we know what is the probability to see another number different than the first one. This will be 5/6, right? So we have 5 numbers that we want to see and 6 total numbers. And this one is 6/6. And the next one will be 4/6. And the last one will be 1/6, because the last one will be observing the last number which haven't been seen. And 5 numbers were already seen. Now we have to take each expected value and calculate it. And these expected values, we will use a geometric distribution to calculate them. And the geometric distribution looks like the following. So we have the probability of an x being equal to k. This will be probability of success times 1 minus p to the power of k minus 1. So a geometric distribution applied in this context will mean that we have a k number of trials, of experiment trials, and we will have 1 success and k minus 1 failures. Of course, it's the opposite order, because first we have k minus 1 failures and then we have 1 success. But because of the multiplication, the order doesn't matter here. And the expected value of such a distribution will be, expected value is nothing more than the weighted sum or the mean. So what can the expected value be? It can be 1 times the probability of k equals 1. It can be that we get a success from the first trial, or it can be that we have 2 trials, 1 success and 1 failure. It can be that we have 3 trials with 2 failures and 1 success, and so on. To be noticed that this goes to infinity. This can also be written as a sum from k that goes to 1 until n. Actually, let's write this to be the infinity. From k, p, 1 minus p, k minus 1. Now, we have to calculate it, and let's write it extended. So this will be p 1 minus p to the power of 0 plus 2 p 1 minus p to the power of 1 plus 3p 1 minus p squared, and so on. Now the trick that we will use is to multiply this expected value with 1 minus p. Now we will have 1 times p 1 minus p to the power of 1 plus 2p 1 minus p squared plus 3p 1 minus p cubed, and so on. And now what we do is that we subtract the first sum from the second sum, and we will get ex minus 1 minus p-ex. And what is happening next is we will be left with only this element. Actually, no, this is the first one. We will have more elements. This is just p, right? And we will have this one minus this one, which will get us p 1 minus p. Next we have this one minus this one, will get us p times 1 minus p squared, and so on. And now we calculate what is to the left. This is so ex minus ex plus pex. And now here we put a common factor to be p. And what is very nice is that these two cancel out, and also p's cancel out, so we are left with a nice geometric sum. And we will do the same trick again, exactly the same trick. We multiply with 1 minus p. And then we will subtract again the first one from the second one. So when we subtract, we are left with pex, like in the above situation. And on the right we will be left with 1, and then these two will cancel out, and these two, and so on. And we will be left, in theory, with the last term, which will be 1 minus p to the infinity. But because 1 minus p is smaller than 0, anything smaller than 0 raised to the infinity will go to 0, so we can just neglect it. So in the end, we are left with ex to be 1 divided by p, and this is one proof that shows that the expected value of a geometric variable is 1 divided by p. So this is what we will use to calculate our expected sum. So I will write it again. I will just copy all of this. Sorry. So we had this thing here. Now we know that the mean, the expected value is 1 over p. Now we can write that ex1 is 1 over 1, ex2 is 1 over 5 over 6, ex3 is 1 over 4 over 6, and so on until 1 over 6. And that will be 1 plus 6 over 5 plus 6 over 4 plus 6 over 3 plus 6 over 2 plus 6 over 1. So that will be that will be 1 plus 6 over 5 is 1.2. 6 over 4 is 3 divided by 2, which is 1.5. 6 over 3 is 2. 6 over 2 is 3. And 6 is over 1 is 1. And this will be equal to 6, 9, 10, 12, 14.7. This is a very nice result. This coincides with other solutions that I've checked on the internet. Now let's think about the general case. When we have xn, we can write this as, here we can write instead of 1, 6 over 6. And we can put the 6 as common factor, and 6 in the general case is n. So let's just write it again. N over n plus n over n minus 1 plus n over n minus 2 until n over 1. We take the common factor. We are left with, I will just write it from the last to the first. 1 plus 1 over 2 until 1 over n. And this is the harmonic sum. So we will have in the end n and sum times sum from k equals 1 to n from 1 over k. And this sum can be approximated with something which I will show now. Just we can take a parallel to a non-discrete sum, which is nothing more than the integral. So we can think, what is the integral from 1k dk, and this is nothing more than natural logarithm of k. Because if you derive ln of k, you will get 1 over k and plus some constant. Now, this is not the exact proof, but I just want to show you the intuition why in other solutions they approximate this sum to be n times, and the sum will be natural logarithm of n plus some constant, which they found out that is 0.577. This is called Euler constant. And in this way you can approximate the result more quickly rather than just calculating this big sum. And this is a very nice solution, I think. So I hope you enjoy it, and see you in another video. Goodbye.